Okay. There are not a lot of people here today.
I think Jeff, Emma, and Tanner will be here though. They're probably just waiting. They weren't seen him.
Andres is here, right?
Yeah.
I think Emma's is here. Jeffrey's not coming to, he told me he wasn't.
Oh, he's not coming today?
They've got a scrimmage.
Oh, okay.
Like you guys, or some kind of thing. So. I don't think he's gonna be here. That's right. All right, what we were doing last time was we said for the simple harmonic oscillator. So I'm just going to do a few problems, and then I'm going to talk about a little bit about another solution to this, to the differential equation that produces this, that describes the simple harmonic oscillator. And so I think last time what we were trying to evaluate was the expectation value of x squared and the expectation value of p squared. We'd already said that the expectation value of position and the expectation value of momentum are equal to 0, right? By symmetry, really. And so then I kind of hurried at the end, didn't do a very good job of this one, and so let's just finish it by starting from the beginning. This is equal to the integral from minus infinity to infinity. We're looking at the 0, right? So psi 0 of x star x squared psi 0 of x dx. Right? And so I have to pull up the wave function for those things, which we wrote down one time or another by the last few class periods. Maybe. I think I was using this beta notation, which is from another textbook. This is just beta. It's equal to this. It just saves you a little writing space. M omega naught over h bar. Just aside, right? So you don't have to keep writing that over and over again. And so this becomes the integral from minus infinity to infinity of psi naught, which is this thing. It's beta squared over pi to the 1/4 e to the minus beta squared x squared over 2. That's that. And then we have x squared, and then we just do it again. Beta squared over pi, 1/4 e to the minus beta squared x squared over 2 dx. And so you can just simplify this a little bit by pulling this beta squared over pi now to the 1/2, because I pick off these two guys. And then I can take the integral from minus infinity to infinity. I combine these two guys, and so I just get x squared e to the minus beta squared x squared dx. That looks right to me. And to evaluate that, we go to this identity. Which which I've probably written down 100 times, but for some reason can't commit to memory. Um, And so we have an n equals 1 in this, right? Because the power of x tells me what my n is. It's 2 times 1 is 2, right? And so this just gives me this integral, my x squared 0 is equal to this thing here. It's beta squared over pi, that's the 1/2, times, so this integral is from minus infinity to infinity, that one's from 0 to infinity, but it's symmetric, all functions are symmetric, and so I'm just going to double this one. And so I'm going to say it's 2 times this evaluated at n equals 1. And so that's pi times 2 factorial over 1 factorial times, so here a is just 1 over beta. Do we agree on that? My integral here is minus x squared over a squared, here it's beta squared x squared. And so I'm going to apply this integral to this form. I have to write a is 1 over beta, right? And so this is 1 over 2 beta to the, so n is 1, and so that's cubed. Did I lose a square root on my pi? So I think I'm good on that. Let me just check this. And so this is just beta over the square root of pi. That's what that is, right? Times 2 times the square root of pi times 2 times 1 over 8 beta cubed. These guys cancel, that cancels with one of those to make that a 2. That cancels with 2 of those to make it 2. So what do I get? I get a 1 over, is it 2 beta squared? And so if I use my beta, it's 1/2 h bar over m. And I do get a warm fuzzy out of this because h bar has units of angular momentum, which is kilograms meters squared per second. And this is kilograms per second because it's the mass times an angular frequency. And so I get a unit of length squared for this, which is what I expect to get when I do an expectation value of x squared. And so then I think they ask you to calculate sigma x, which is the uncertainty in x, which is the square root of this guy minus this guy, which just ends up being the square root of this guy because that guy's 0. All right, so the uncertainty in x is just the square root of h bar over 2m omega naught. If I taught this class 6 times, I would be able to probably say something interesting about that result. Or even just once. Probably some significance to that. I mean, this is telling you the spread of that the position variable. Think about it. So that's x squared, or that's expectation value of x squared. Right? We expect it to be non-zero, right? Because the wave function looked like that, right? And we're asking, what's the absolute value of its position rather than what's its average position, right? What's the absolute value? And so it's almost like you integrate this and take the centroid of this, right, where this thing balances, and that's what this thing is giving us essentially. All right. So let's do the other one, p squared. Or p, we did p, and so now we do p squared. And so the expectation value for p was 0, also by symmetry, which we said a minute ago. And so p squared is h bar over I d by dx on h bar over I d by dx. And so that's equal to minus h bar squared d squared by dx squared. And so if I wanted the expectation value for that for the ground state, P,
Did you forget your star?
I did, and I should probably have a parentheses there, right? I'm getting a little lazy with the stars, aren't I? Because we're choosing real phases all the time. We don't have to be. So. Thank you. And so this just becomes minus infinity to infinity. So this is beta squared over pi. So 1/4 times e, so minus beta squared x squared over 2 minus h bar squared d squared by dx squared. Acting on the same thing. Beta squared over pi 1/4 e to the minus beta squared x squared over 2 dx.
Oh yeah, I see. So you didn't need the star.
Is that good?
No, I just understand why you didn't put the star.
Oh, yeah. No, it's good. I'm glad it should be there. The star should be there, right? Even though we know it's a real function, right? If you're writing it abstractly like that with just the wave function there, it should really. So this is beta squared over pi again. So 1/2. I can't combine these terms yet. I can pull a minus h bar squared off from. Right? And then I still have this minus infinity to infinity e to the minus beta squared x squared over 2. But now I've got to operate on this thing, d squared by dx squared on e to the minus beta squared x squared over 2 dx. Right? I've got to let that thing operate before I can carry out an integral. And so I'm just going to pull that outside and do that for a second. Right? D squared by dx squared on e to the minus beta squared x squared over 2 is equal to d by dx on the first derivative of this, which is minus beta x e to the minus beta squared x squared over 2. How do you feel about that? It's
Beta squared.
a beta squared minus 2 cancels. I get a minus beta squared x. Are we good? Okay. And then I got to differentiate that. So I'm going to pull the minus beta squared out. And I'm going to say it's the first times the derivative of the second, which is x times minus beta squared x e to the minus beta squared x squared over 2. Right? It's the first. I just have that. It's the first times the derivative of the second. We already know what the derivative of the second is, this thing in parentheses, right? Plus the second times the derivative of the first, so plus e to the minus beta squared x squared over 2. Are we good on that? I lost everybody. Right. I just factored the e to the minus beta squared x squared over 2 out from each one. This guy has a 1. That guy has a minus beta squared x squared. And so I get this. And so now if I go back to my b squared here, I'm going to take what I have here, and I'm going to stick it in here. And so I have minus h bar squared. And so beta squared over pi to the 1/2. Right, that takes care of what's in front of the integral. I'll leave the stuff inside the integral the way it is for a minute, so I get all organized. Right, this is e to the minus beta squared x squared over 2. That's what's on the left, and then I'm going to put in everything I just calculated. This bracket, so it's minus beta squared on minus beta squared x squared plus 1. Right? E to the minus beta squared x squared over 2 dx. I'm going to bring the beta squared all the way out, and for now I'll just so you can see where it went. This guy's coming all the way out because he's just multiplicative, right? And I have this beta squared over pi. I could probably simplify that a little bit, but let's just leave it for now so we can see it all, right? Times the integral from minus infinity to infinity of, and so it's, I can do it this way. I can say it's 1 minus beta squared x squared e to the minus beta squared x squared dx. these two guys make this. This guy is here, this guy is here, right? And those two guys come. And so I can do a little simplification here if I want to, right? I can cancel the minus signs out here. If I want to, I can write this as h bar squared beta cubed over the square root of pi. Right, beta squared square root just gives me a beta. Minus signs cancel. I get that. On these two integrals, the first one is the integral from minus infinity to infinity of e to the minus beta squared x squared dx. That's this guy. Minus beta squared times the integral from minus infinity to infinity of x squared e to the minus beta squared x squared dx. For homework, we're going to recalculate this one. Just kidding. What a mess this is, and it's such a simple wave function, right? That would be a nightmare. Even one would be ugly. So we get p squared 0 is equal to h bar squared beta cubed over the square root of pi times, so this integral, and so we can go back to our side integral, right? Where should I write it? Maybe all the way back to the beginning. The square root of pi is really convenient because it cancels the other square root of pi. And so this guy becomes twice, since it's symmetric, the evaluation of this at n equals 0, right? So this is just 1, because 0 factorial is 1 and 0 factorial is 1. So it's the square root of pi times 1 over 2 beta to the 1. And it's going to be minus beta squared times this guy. Right? This is the n equals 1 version. And so this is the one we just calculated a minute ago. It's a square root of pi times 2 factorial over 1 factorial. I can just say 2 over 1. Times, and this is 1 over 2 beta cubed. And both of these are this is the 2 that changes the minus infinity to infinity integral to a 0 to infinity integral. So both of those get multiplied by that. So I'm going to cancel the square roots of pi. That simplifies my life a little bit, right? This is, so that goes like that. This guy cancels that one. This first guy just becomes a 1 over beta. Minus, and so this is a beta squared times 2 times 2. So this is, the second guy becomes 2 beta squared times 2 times 1 over 8 beta cubed. It's this 2 times beta squared times this 2 times that quantity in the bottom cube, which is 8. One of the betas here cancels with that one and that one. I get 1 minus a half, which is a half. And so I just get this quantity. That was what my beta was.
So it's 1/2 h bar m omega naught.
Yeah. It's always worth checking the units, right? So this guy is mass times length squared over time times mass times 1 over time. And so it's equal to mass squared, length squared over time squared, which is momentum, right? It's mass times velocity, quantity squared. So at least our units come up right. All right, and so now we can say, right, the expectation value, or the uncertainty, that's the expectation value for p squared. The uncertainty in the momentum is the square root of p squared minus p squared. And so that's just the square root of this thing, right? It's the square root of h bar m omega naught over 2 minus 0, which is just the square root of h bar m omega naught over 2. That's a slog.
Uncertainty principle thing and see if it satisfies that.
Say again?
The uncertainty principle, isn't that where we just multiply those two things together? And it's uncertainty principle?
Sigma p sigma x?
Yeah.
Yes. Did I lose my sigma x?
I got it. It is square root of h bar over 2 m omega. Can't remember.
H bar,
over 2 m omega.
what do we get? H bar over 2?
Hey.
Yay! We possibly did that right.
Can I ask you a quick question?
Yeah.
In case I forget before the end of class, for our formula sheet for our test on Wednesday.
That's a good question. I don't know anything about it.
Cool.
What does she normally give you guys? Does she give you a formula sheet?
It's been so long. I had to remind her last year.
Yeah, she give us modern.
Did
Huh.
you give it like ahead of time so you could set it?
She gave us one at the beginning of the semester.
Oh,
Might be fine.
it might just be that huge one.
Yeah, it's that big
Yeah,
one,
that
yeah.
big old one.
Uh-huh, okay.
But it tells you like which chapter, like it'll be like chapter 1 and show all the equations in chapter 2.
Okay, that's handy.
Hey, what homework did y'all get back? Did you get 1 and 2?
Yeah, I
Yeah.
got two. Did you not get both?
I just got 1. Oh.
Oh, weird. Did
And I'm like,
get two?
yeah, I'm like 2 weeks grade. She lost.
Well, if you got the grade.
That's not good grades. Oh. I think I need to tell her to go for something, because she had said, where's problem 1.10? 0 out of 8. On the back. It's just right here. I don't think she saw it. Unless she just saw it and like, nah, that's garbage.
That's why I'm always at the bottom, like, rest on the next page, and I'm like,
Oh
going
my
back to the page.
Yeah, I'll like mark it out and be like, look on the next page.
Yeah. That'd be funny. Alright. With that, next time, I just think it's funny.
How do you guys think you're gonna study for this test?
Go over the homeworks.
Yeah.
Probably just read a little bit too.
And look at the formula sheet.
Yeah, and I might just be like,
The study questions too, that she puts out, right?
like, well, those papers you gave us, that she gave us, at the beginning of the semester, they have study questions.
Yeah, those.
Yeah.
Okay,
But,
need to look.
no, no.
I don't think I'm gonna do too great on the test.
I don't know, I'm taking it back, but I want it to be at least over like a 4. You know, something I can like maybe recover from. It'll be bad, but.
So I just called her, and she said there's a formula sheet on Canvas that you get for your
Oh,
exams.
great.
And so if you can't find it,
Yeah.
I'll have her just like highlight it or something, say it's here, it's in the file section somewhere in there. And she gives, it's just a stack of equations, she said, for the whole semester, and you can use them on your exams. So
Great.
hopefully that'll,
Probably study questions.
Yeah, they are.
Oh, great.
there was a problem in here that I just wanted to talk about for a minute, maybe we could solve it. But I just wanted to, we're gonna see it. Give me a second. Oh, here we go. It's 14, I don't know if she assigned it. Did she assign it?
Your
Doesn't
homework.
You have to show me the problem.
Let me look.
Let's just talk about it for a second. And, it says in the ground state harmonic oscillator, what is the probability? It's 3 significant digits of finding a particle outside the classical region. So classically, the harmonic oscillator has an energy E equals 1/2 K A squared, right?
This is 2 2.14.
Yeah,
No, she didn't decide.
right. Where A is the amplitude. Right, we just said, this is what we were talking about last time. You stretch the oscillator out, right? You pull it out a distance A, and then the total energy at that point is 1/2 kA squared. That's the maximum displacement you get, right? A classical oscillator will never get outside there. It'll oscillate back and forth between the 2 points A, and it can't go beyond. That's the classically allowed region. But a quantum mechanical particle can actually go beyond where it's energetically allowed to go, right? And so the question is, so how do we figure that out?
Well, we'll have to eventually integrate psi squared, like from in the CFR.
Yeah, in the allowed part, right? So what we know is that the integral from minus infinity to infinity of psi naught star psi naught. I should call it psi 0. It's not psi naught. Dx is equal to 1. Right? And what they're asking us for is the probability that it's outside of that region. And so what we can say is, look,
Do we agree?
this is the probability that it's between minus A and A. And so 1 minus this is the probability that it's outside that region. Right? A is equal to the so this is how we wrote the potential energy curve for the harmonic oscillator, right? 1/2 m omega naught squared A squared. And so we can say A is equal to the square root of 2e over m omega naught squared. Right? And so we can integrate 1 minus the integral from minus A to A of our quantity, right? It's beta squared over pi, so 1/4 times e to the minus beta squared x squared over 2 times beta squared over pi, so 1/4 times e to the minus beta squared x squared over 2. where A is this thing. For the ground state, the energy is 1/2 h bar omega naught, and so we can substitute in. And the tricky part about this one is that you then have to be able to evaluate this integral between finite limits. And so that's just, that's another table lookout, which I don't have. So that becomes, I don't know, the probability outside is equal to 1 minus the integral from, can I do that? Yes?
Yeah.
This integral, unfortunately, doesn't follow the behavior of the formula in the back of your book unless they have it back there. Do they have it back there for a finite range? No. Eh. What's that called? It had it, I just want to talk about it for a minute. Anyway, normal distribution or error function, that error function. All right. I'm just going to write. This is terrible. I'm going to show you what it is on Monday. But you can look up. You can look at these. This is an integral lookup, a table lookup, an integral. You can evaluate it. All right. I think I'm going to stop. I want to. I'll spend a few minutes talking about this on Monday. I think whatever we've gotten to today is what's on the test. All right. I wanted to say. She wants me to talk about the analytic form of the solution to the integral, the other solution to the differential equation that describes the harmonic oscillator, because it describes a set of polynomial functions called Hermite polynomials, which show up occasionally in physics. Although the only place I ever see them is in the harmonic oscillator problem. Do you know Legendre polynomials? Have you run into those in your classes? Hermite polynomials is sort of a classical set of polynomials that show up in various types of problems. And if you look at all of these wave functions, they all have, you know, size of n has something that has a bunch of polynomials in it, and then it's got an e to the minus beta squared x squared over 2. And the first guy just has a 1 here. The second guy has an x here. The third guy has like an x squared plus a constant. The fourth guy has an x cubed plus an x. The fifth guy has an x fourth plus an x squared plus a constant. That series of functions that increase in n are called Hermite polynomials. Once you sort of, you know, get their normalization right. And so these solutions are often written in terms of Hermite polynomials. Since I have a minute, let me just write that part of it down. So,
So are you saying you don't think anything will be included on the test past what we did today?
no, I'll just make sure it's not.
Okay,
All right?
sounds good, thanks.
So this is size of n of x is equal to, and so it's just got some normalization function. Each one of the simple monotonic wave functions has to be normalized independently. And then it's multiplied by this Hermite polynomial, which it has the behavior I just described of beta x, and then e to the minus beta squared x squared over 2. And so h of 0 they use just any generic variable. It's equal to 1. h1 of c is equal to 2 times c. h2. This is just whatever's in the argument, right? Is equal to 4 times this guy squared. I'm really butchering it. Minus 2. h3 is equal to, so it's 8 cubed minus 12. I don't know why they picked the worst looking variables. So this is a 16 fourth. You can sort of see a pattern here, minus 48 squared.
Minus or plus?
Minus, what did I say, plus? This is minus squared, and then plus 12. The coefficient for the largest is 1, 2, 4, 8, 16. And this is 6, 4. I don't know. I don't see the pattern, but there's a generating function for them so that you can knock them all out. And so you can just write the solutions as similar oscillator this way, where all these guys are Hermite polynomials. Did you guys get any homework problems on these guys?
Not yet, unless homework 4, which I just looked at.
Okay.
Yeah, I haven't either, so.
All right. That's all I've got. Let's stop there.
Hey, do you have my homework 2 as well? Because I only got homework 1, but if not.
Did everybody else get homework 2 back?
I did.
You did?
Yeah.
Maybe you stopped by my office. It's possible it got stuck in a pile somewhere.
I'm gonna just put it in the group chat, because Jeff asked me to.
Did you guys already do this problem today? What we did today?
I don't think so.
No?
Yeah, homework 4 is like number 10 and question 10 and question 11 of chapter 2.
Okay.
Oh yeah, Dr. Trail, so.
Hang on a second, hang on a second. So let me just turn this off. I was recording this for Jeffrey.
Ah, right.
Everybody say hi to Jeffrey.
Hi, Jeffrey.